Are there any questions before we start? Yes?
Problem 4.
Okay, I have no problem here with me,
They
but tell me what the problem is.
They want us to find the F1Z and F2. What is the meaning of this 2F? Just the question says find F1Z and F2Z.
Mm-hmm.
Yeah, so I mean, just what is
It's from the book, which, I expect the problem might be from the book, I suppose. Yeah, so anybody else who has worked out what he's asking is F1 and F2 are two signals, F1N and F2N. Is there anything denoted F1N and F2N or no?
I think it's just like the transfer function. It's like the transfer function of X over U.
Transfer. Oh yes. So the f of z vector, yes. So in the chapter we talk about the f and g, which are two different quantities, right? So yes, okay, yeah. So yes, so that's okay. So the f is the transfer function from the input to the state, right? Yeah, okay. So f of z is the state z transform x of z divided by u of z. So that's what is denoted as f of z. Okay, and then g of z is the transfer function from the state to the output. Is that so? So when you think about this f, the vector, I guess the f1, f2 are the state 1 input to state 1, input to state 2, etc. Is that making sense? Is that clearer now? Okay, very good. Any other questions? Okay, so if not, we will continue with our lattice filter content. So at the end of last class, we almost completed deriving the so-called basic lattice filter. So we derived two equations by following this process. If I go back to, so there is a standard process, okay, there is a standard process to follow. So we start with the degree reduction equation, and then from the degree reduction equation we take the reverse polynomial of that equation, okay, and then from that equation we get one equation. So there is little more simplification, cross multiply, take this to the other side and we get that equation. Okay, so then the next, so that's kind of think about that as step 1, and step 2 is to step 2 is to substitute that psi n star in the original equation psi n minus 1 is z. So that's the original equation. So substitute that here, and then we get one equation, and then from this equation itself we have one other equation, and these two equations are sufficient to describe the equation for one stage. Okay, so yeah, so there are some more things that we'll talk about. So there is really, there are many technical derivations in this chapter which you should carefully read, but there are also many technical concepts, not just derivations but concepts that we will try to discuss in the class as well. So before I talk about the so-called normalized lattice, maybe it is a good time for me to spend a little time on the FIR lattice before I talk about the normalized lattice. Okay, so we'll come back and talk more about these things. So there are this whole concept of pushing these delays to the bottom path. So instead of delays going on the top path, if I just do a retiming step, take a retiming cut set, move that from top wire to bottom wire, and that changes numerous things. And the reason we try to do that is to expand the numerator polynomial with respect to the bottom path. So we'll talk, I think I talked briefly, but we'll talk more about that. So let's start with the FIR lattice, and then we will talk about normalized lattice. So FIR lattice, and let's call that the basic lattice structure. So the so-called, when we talk about basic lattice filter, that's the structure. Okay. So what we want here is a stage, a section or a stage or a part of the filter where the data are moving in both directions, right? So we want to start with, so what we want here, so if you recall here we have psi n star, and then psi n minus 1, psi n minus 1 star. So in the basic FIR lattice, okay, so we are interested in the degree going up by 1. So in the IIR, we are relying on the degree reduction process. So the degree goes down by 1. In the FIR lattice, the degree keeps increasing by 1. So if I want to just start with this z psi n minus 1 and z psi n minus 1 star, the reverse polynomial, and this then is after a delay, that is psi n minus 1 star. So so the first thing that I need two equations, but I can just use this equation as it is. Okay, so if I just use that equation, okay, so that is one equation where I can compute psi n star, which is psi n minus 1 star, so that's this one, plus this quantity, which is z psi n minus 1 multiplied by kn. Okay, so that completes that path. The next equation, I can start with this equation number 1. So let's start with that. So from equation 1, so take this z to power minus 1 to the other side. We have psi n minus kn psi n minus 1 star is equal to z times psi n minus 1. So take this z to power minus 1 to the left side. Okay. And then we have okay, so psi n is z times psi n minus 1, that's this point, plus, so this plus kn times psi n minus 1 star, so that's kn. Okay, so those are the two equations that complete the FIR lattice, and so if we have nth order FIR filter, then we can compute the k coefficients and then repeat this process from kn, k1 through kn. So so let me, without drawing these diagrams, so let me show you in the textbook. Okay, so if you look at the FIR lattice structure here, so the degree that we start with in the beginning is z to power n times psi 0. Psi 0 is a constant, okay? Psi 0 is a constant. And then, by the way, the stage that I just derived is the last stage, using z psi n minus 1, z psi n minus 1 star, and compute psi n and psi n star. So that's what we just derived. Yeah, so that's the very last stage corresponding to the reflection coefficient Kn, and so psi 0 is a constant, it's just a polynomial with a constant term. Psi 0 star is same thing because both are constant terms, so this point can be connected to the bottom because these are the same polynomials, and then we keep reducing the degree by keep well, I guess, yeah, I'm not sure if we are reducing degree or not, but the k coefficients k1, k2 up to ki and kn, these are the stages, and the k coefficient for the ith stage ki, both going here. So the example that shows the that 345.1 example that we had, this is the input going down, and then there are the delays in the beginning of each stage, Okay, so that is the FIR lattice. So anytime we derive the IIR lattice, the same equations can just be changed just a little bit. As you can see, one equation just state the constant, the other one take this to this side and then express IN, so that's the other equation. So yeah, so there isn't really much difference. Every IIR lattice equation can be reformatted to FIR lattice. Okay, so with that, I think we talked about a couple of things briefly, and no matter how much I talk about, I think the real practice will come with homework. So okay, so let me start with the normalized lattice, and then we'll talk more about the concepts of expanding the numerator and what the orthogonality and things like that. So we'll take a brief detour from that. So how can we derive the so-called normalized lattice? So in the book there are 4 types of lattice structures. This so-called basic lattice, which we just looked at, is based on the polynomial psi, the normalized lattice, and there is a scaled version of that called scaled normalized lattice. So these are both based on the degree reduction process called phi, which is what we started with in the beginning of last class, right? So okay, so that's the degree reduction process for the normalized lattice. We'll in fact talk about that immediately after I write down the last structure, this so-called one multiplier lattice. And that's based on another degree reduction process, which is based on the polynomial degree reduction process called lambda. Okay, so so these are all related. It's not that they are that different from each other. So if you look at the phi polynomial degree reduction, the denominator is square root of 1 minus kn squared, and if you look at the psi polynomial, and instead of square root, this is just itself 1 minus kn squared. That's the main difference. And in the one multiplier lattice, that denominator is simply 1 minus epsilon n kn, where epsilon n is plus or minus 1. So everything is same. So this is I'm not going to write down all the details, but so everything is same, divided by 1 minus k n or I squared, and this is all same thing, 1 minus ki squared square root, and this is all same thing by 1 minus epsilon I ki for the ith stage. So these are the denominators, and they're slightly different, and the epsilon is plus or minus 1. And so so why people have been interested in all of these, as you can see that the basic lattice structure requires 2 multipliers per stage. So whether we are doing FIR or IIR, so we need 2 multiplications, Kn going down, Kn going up, so 2 multiplications per stage. The normalized and scaled normalized, these require 4 multipliers per stage. But the main advantage, because this is normalized, so the K matrix will be the identity matrix. That means the covariance of the state, the power of the state or the covariance of the state for each and every state will be 1. Whereas the basic lattice, the K will be a diagonal matrix, but not identity matrix, because the states are orthogonal as opposed to orthonormal. And the one multiplier lattice, again with some tricks, we can reduce the number of multiplications per stage from 2 and 4 to 1 multiplier. So that's kind of the main advantage. Of course, it's not orthonormal, yet it is orthogonal. It's orthogonal with some other scaling factor, the scale factor. Okay, so so with that, let's start with how do we derive same kind of process here, follow the same process and derive 2 equations to describe the normalized lattice. So the starting point for normalized lattice is that degree reduction that I talked about. Okay, so that is our starting point, and we will start with that equation and then go through the same process. So the first step is to compute the reverse polynomial of this quantity. So that's kind of the first process. And then once we complete that, okay, so we will, let's start with that equation. So the definition of the reverse polynomial phi n star, this phi n star is z to power n phi n 1 by z. All we are now doing replace n by n minus 1. So replace n by n minus 1. And the reverse polynomial of degree n minus 1 is replace n by n minus 1, n by n minus 1, and 1 over z. Okay, so then this is equal to z to power n minus 1 times, in this equation wherever there is a z, replaced by 1 by z, so z to power minus 1 is replaced by z, phi n, z replaced by 1 over z minus kn, in everything here z replaced by 1 over z, z to power minus n, phi n, 1 over z becomes z divided by 1 minus kn squared, square root, which is z to power n, n minus 1 plus 1, so this product is z to power n, phi n 1 over z minus, when I multiply this with that z to power minus n cancels out with that z to power n, and we are left with minus kn phi n z by 1 minus kn squared, square root. Okay. And this quantity here, I can put that back as a simply phi n star. That's the reverse polynomial. Okay, so now I can write down now phi n star, so this quantity, take this to the left side and take this to the left side, so this is equal to 1 minus kn square, square root times phi n minus 1 star plus kn phi n. Okay, so that's, so take this to the left, take this minus to the left, becomes plus, and then phi n star is this quantity. And what is the next step? So once we do that, the next step is to take that phi n star and substitute here, substitute in this expression. Okay, so that's the next step. So phi n minus 1 is equal to z to power minus 1 times phi n minus, okay, minus kn times this whole thing. Okay, so minus kn times phi n star. So first of all, let me write down the second term first. Minus kn times plus kn is minus kn squared phi n, then minus kn, 1 minus kn squared, square root phi n minus 1 star divided by 1 minus kn squared square root. So from the two quantities here, I can take phi n outside a bracket, and that becomes phi n taken outside a bracket 1 minus kn squared, and then I can cancel out the 1 minus kn squared square root, and then that becomes square root. So 1 minus kn squared cancelled out by square root and remains 1 square root. Okay, so some arithmetic, nothing that difficult, but we have to go through these steps. So let's see finally what we have. We have, if I bring this z to power minus 1 to this side, I have z phi n minus 1 is equal to phi n times square root of 1 minus kn squared minus kn phi n minus 1 star. Okay. So that's our first equation. So that's one equation. Okay, so that is one equation. We surely need that equation. We need to derive the other equation. So the other equation phi n star is equal to 1 minus kn squared phi n minus 1 star plus kn phi n. So that is the second equation. Okay, let's call this one first and this one second, and those should be two equations. And if I use those two equations to write down okay, so now let's see if we can complete these equations. So phi n star, is equal to 1 minus kn squared times phi n minus 1 star. So 1 minus kn squared square root plus kn times phi n plus kn times phi n. Okay, that equation is complete. Z times phi n minus 1, which is here, is equal to phi n times square root of 1 minus kn squared minus kn phi n minus 1 star. So this is minus kn. Okay, so that's the basic stage of the normalized lattice. So if you recall, the k coefficients are always less than 1 in magnitude, so which means that the 1 minus kn squared also is less than 1. So if you think about these coefficients, these are not only just less than 1, but if you think about the reflection coefficient ki as cosine theta, then 1 minus ki squared square root is sine theta. So these could be realized using quadratic operations. And we are not talking about this now, but some of you may have heard of coordinate rotation digital computer, quadratic operations that can compute all kinds of trigonometric and trigonometric with hyperbolic, tan hyperbolic and sine theta, cosine theta, all kinds of functions. So these sine and cosine functions could be computed using quadratic operations. So that's kind of one thing to observe. Okay, so okay, we'll talk more, but again, the same concept of okay, let me just show some examples and then we will briefly talk about the one multiplier lattice. Okay, so if you look at this lattice stages, not bothering about this part here. Okay, I guess I should show you the whole structure here. So phi n, start with phi n, the degree goes down n minus 1 all the way to phi 0. Phi 0 is a constant, so that's fed back to complete the IIR. And the one such stage that I just derived is shown here, the delay is on the top. Okay, and then we can expand the, if there was a numerator, we can expand the numerator from these polynomials. So for example, we talked about expanding the numerator polynomial in terms of phi n and this point phi n minus 1, phi n minus 2, etc. And again, we'll talk more, but we can push this down, the delay comes down, and if we do that, then that's what you see on the diagram here. Okay, no, that's not this diagram. So the delay is on the forward path, and we are expanding the C0, C1, C2, C3 on the from the top path. I don't know if the book, yeah, here, okay, I see. So, so we could again push the delay down, and then the delay is now on the bottom path instead of going on the top path. And if you think about the polynomials now, starting with, because I don't have the delay on the top path, so this z, so we don't have that delay to bring that to phi n minus 1. So this is z phi n minus 1, and that's the first stage output. The next one becomes z squared phi n minus 2, and very last polynomial z to power n phi 0, and that the phi 0 is just a constant, so then that can be connected back to the backward path, and then the then we get phi n star at the end. So that's what we get. And so technically speaking, why is it? Why are people interested in pushing this delay down and expanding? So if we were interested in, and again, there isn't really a lot of reason why one is better than the other. They're all equivalent. The transfer functions are all equivalent, but there might be some difference in finite word length properties. But I think the real motivation for studying so many different structures is likely more academic, and there is something to be said about academic curiosity, very important part of learning. And so academic curiosity is definitely, even though it's not always useful in improving something or it's just as good as something we know before, but it's still an important part of learning and research. Okay, so so the reason why we are interested in pushing that delay down and expanding through the bottom path, no matter what structure we are using, is simply because the polynomials, if we had So if we wanted to expand the numerator from these polynomials Pn star, Pn minus 1 star, Pn minus 2 star up to P0 star, these do not form an orthogonal or orthonormal basis set. The phi polynomials form an orthonormal basis set, but these reverse polynomials do not form an orthonormal basis set. So the numerator shouldn't be expanded in terms of that. But that said, if we push the delay down, phi n star z times p n minus 1 star z squared times phi n minus 2 star all the way up to z to power n phi 0 star, these indeed form an orthonormal basis set. They do. And so I won't prove that in this class. And so there is, I believe, there should be one appendix talking about this more. And I don't really want you to spend more time on these things. But yeah, so there is, so these can be a bit involved, but yeah, if you really want to, I am intentionally trying to avoid these formal definitions of inner product, and I'm just saying what is orthogonal and orthonormal. But that appendix D is definitely a resource, and if you want to spend time and if you are not sure and you want to really understand, then yes, so by all means you can go to that appendix, and there are more things there. I think, yeah, I don't really plan to talk about those. I think my goal is to see how we can derive the structures and understand their properties. Okay, so that's kind of one technical part, is the reason we push the delay down, because then the modified reverse polynomials become orthogonal. So that's simply just mentioned in this section here, just mentioned, and that's enough for this class. This p n star z times phi n minus 1 star z squared times phi n minus 2 star up to z to power n phi 0. Okay, should be phi 0 star, but phi 0 star is same as phi 0 are orthonormal. And similarly, the polynomials I n star z times I n minus 1 star z squared times psi n minus 2 star, etc. are orthogonal, not orthonormal, but orthogonal. Okay. So, okay, so that's the reason why when we push the delay downstairs, which is equivalent to retiming process, it maintains the orthogonality or orthonormality of those polynomials. And that's why we can expand the numerator with respect to those polynomials. Okay, so let me just talk about the so-called one multiplier lattice and how it is indeed possible. I mean, as you can see here, each stage requires 4 multiplications, 1, 2, 3, 4. And the so-called basic lattice requires 2 multipliers per stage. So it does turn out that it is possible to derive a structure where we can just require 1 multiplier per stage, and the so-called 1 multiplier lattice structure. Okay, so these are based on this polynomial reduction process called lambda. So lambda n minus 1 is equal to z to power minus 1 lambda n minus kn lambda n star by 1 minus epsilon n kn. Okay, so that's the main difference in the way we derive these degree reduction processes. So everything else in the numerator is the same. So if we start from very beginning with the nth degree polynomial, of course the subsequent polynomials will change completely, because of these scale factors, but the normalized lattice phi polynomial is square root of 1 minus ki squared. This is 1 minus k I squared, and this is 1 minus epsilon iki. And so this epsilon is not just an ordinary quantity, it is a very special quantity, that is plus minus 1, plus 1 or minus 1. One important thing to think about is the epsilon squared is 1, and we will see how that can help us derive the lattice structure that requires only one multiplier with respect to each stage. So our process of deriving the one multiplier lattice is again, we really follow the exact same process that I was following right now. So start with, so if you recall what we did, we either the basic lattice or the normalized. So we are always starting with the reverse polynomial lambda n minus 1 star, simplify that gives one equation, and then get from that this lambda n star, and put that back here. That will be the second equation. So the process is exactly same. So we start with this lambda n minus 1 star. Okay, from this now I can just replace z by 1 by z. Okay, and then lambda n, z replaced by 1 by z. And this quantity was z to power n, lambda n, 1 by z, and then when I take z replaced by 1 by z, so this becomes z to power minus n, lambda n z by 1 minus epsilon n kn. So this is z, exact same thing, z to power n, lambda n, 1 by z, which by the way you can see is lambda n star, and that is, and then minus kn. What is this quantity? Z to power minus n, z to power minus n cancelled out with z to power n, and so we are left with lambda n by 1 minus epsilon n kn. And as I mentioned, this quantity is lambda n star, and then bring this to the left side and this to the left side. Same process, exact same process. So we have lambda n star is equal to 1 minus epsilon n kn times lambda n minus 1 star plus kn lambda n. Okay, so bring this to left side, bring this to left side, so lambda n star is equal to that quantity. Okay, and then so that equation would be perfectly fine, but wouldn't lead to the one multiplier structure. So to get to one multiplier structure, I can then say that this is equal to, so multiply these two terms, so lambda n minus 1 star minus epsilon n kn lambda n minus 1 star plus kn lambda n. Okay. So then that's lambda n minus 1 star minus plus kn times lambda n minus epsilon n lambda n minus 1 star. Okay, so that is our one equation. So it took us some time to get there, but yeah, that's the first equation. The second equation can be obtained by just substituting, I don't have to get to this point, but simply substitute this lambda n star here. So if I do that, just substitute this quantity here. I don't really need, there's a reason why we got to that point, but yeah, so I can then write down, so lambda n minus 1 is equal to z to power minus 1 lambda n minus kn. Okay, now let's times lambda n star. Let's take that equation here and just multiply that out. So minus kn, so I have this kn here. Again, I can take this term first, minus kn squared lambda n minus kn times 1 minus epsilon n kn lambda n minus 1 star. Okay, so we now multiplied both terms. Yeah, and then all divided by 1 minus epsilon n kn. Alright, so now, so just as I did in the previous case, I can take lambda n outside the brackets. So from these two, so that's lambda n times 1 minus that. Okay, so that's simple to see. Now here is the trick. It is possible to cancel out 1 minus epsilon n kn in numerator and denominator. Of course, I can just cancel this out here, and I can cancel this out here also. But it's not obvious. How do I cancel this with this 1 minus kn squared? So this one cancelled out with that one. And how is this cancelled out? The first thing to observe is that epsilon n squared is 1. Okay, so just multiply this quantity kn squared by epsilon n squared. And then I can just cancel this out because it's a minus b times a plus b a squared minus b squared, so 1 plus epsilon n kn. Okay, so that was the trick there. Is the trick clear? Okay, so then I can say that we have lambda n to power lambda n minus 1 is z to power minus 1 times lambda n, okay, and then I multiply these two out, lambda n epsilon n kn minus kn times lambda n minus 1 star. Okay. Okay, so that's good. So we are interested in one multiplier lattice. Okay, so that's kind of what we want to see, how we can realize using one multiplier lattice. So I still have to go through this. So this is lambda n plus epsilon n kn taken outside a bracket, lambda n minus, so again I place an epsilon n squared here, so that I can take epsilon n, kn outside the bracket, and then we are left with 1 epsilon n okay, so what have we gained with all of these? Okay, so now let's see if we are able to realize these two equations. Where was I? 22 point, yeah, so these two equations. So 1, 2. Okay, how can we realize these two equations using one multiplication? By the way, we don't count multiplication by epsilon n because that's just plus or minus 1, and that's not a real multiplication, so that's just add or subtract. But the most important thing to observe is that this quantity is in both places. If you are wondering why we had to go through this couple of times, replacing epsilon n squared and here, is because we are interested in, once we use that multiplication by kn, it has to be part of both equations because we are only using one multiplier lattice. And that whole part, and the reason I took out the quantity out of here and then take something out of these two terms, is to really make use of that term to compute the second one. So, okay, so now let's see if I can complete the structure. So we start with lambda n and lambda n star. Okay, so the first equation says lambda n star is equal to lambda n star is equal to lambda n minus 1 star. Okay, so we just add that, plus kn times lambda n minus epsilon n lambda n minus 1 star. So multiply here by minus epsilon n. So lambda n minus epsilon n times that, multiply by kn, and add that here. Okay, so that is lambda n star. Okay, what is lambda n minus 1? Lambda n minus 1 is, so whatever is that red quantity, the red quantity is here. Lambda n minus epsilon n times that times kn is here. Now I multiply that by epsilon n, add lambda n to that. So take this lambda n and add to that, and then go through a delay, and that's lambda n minus 1. Okay, so then you will see that only there is one multiplication kn. Right here there are two add or subtract because of this epsilon n and minus epsilon n. So that is the one multiplier lattice. Again, the delay could be pushed down on the bottom path, so that's kind of the same reasoning. But yeah, so this is the one multiplier lattice. Now we don't need more than one multiplication. And that was only possible because of that special quantity epsilon n, the property that epsilon n squared is 1, and we had to make use of that property a couple of times. You can see that I used epsilon n squared to factor out that quantity here, and then used another time here to take out epsilon n again outside a bracket. So by doing that, we are at the end we are able to get the one multiplier lattice structure, which requires one multiplication per stage. Okay, so we have covered the very basic structures of all, well, scaled normalized. I didn't talk about that, but yes. But anyway, the inner part of the core part of the structures we have now completed. Any questions about these things? Yeah.
So, I guess just to give myself a higher level understanding,
Yeah.
why would you implement something with a lattice filter rather than just direct or any of the other ways that we've talked about?
Yeah. So the question is why people became interested. I mean, of course, there was a lot of interest in those days in using lattice structures, and these structures have certain very nice properties, and particularly with normalized lattice, the coefficients are always between -1 to 1, the k coefficients. So these were already normalized with respect to the state variables. So that means there wasn't really any need to do any extra scaling on top of these. So these were already scaled. And so if people were interested in implementing using programmable DSPs, the direct form filters were really not suitable for programmable filter implementations, especially for long tap filters. Because if you didn't do scaling, especially scaling in a systematic way, the output would all be garbage. And so yeah, so those so there were interests in lattice filters for two reasons. One, even though it requires more multiplications, but these are already scaled, and these means we could always have a certain number of word length, and the one sign bit, these would always work in the programmable DSP or in fixed point. The other reason which is why people became interested in lattice filters is because the lattice structures could be used to model human speech. So if you think about the generation of the vowels and consonants, and so how the sound comes out of the throat, and that could itself be modeled by lattice parameters. And that means by using random variables or the random processes as input to a lattice filter, one could synthesize speech. And so in a lot of speech applications, there was interest in synthesizing speech using lattice filters, again for for variety of reasons. And one of those reasons was in a speech codec, you could then just transmit just the k coefficients. You could transmit, instead of transmitting the speech itself, you could just transmit the k coefficients and that are associated with that vowel or consonant, and that would lead to speech compression. And so there were a lot of different reasons, and again it became, the Schur polynomials themselves became of interest in adaptive filters. And so if you take a class on adaptive filters, you will relate these concepts, and a very different community working independently not interested in digital filters at all, but interested in adaptive filters. And you will see these lattice filter concepts in the adaptive filter class. So if you are using the Levinson-Durbin algorithm, you will see the same kind of polynomials being used there as well. So two different communities working on similar kinds of mathematical derivations. So yeah, so there has been quite a bit of interest. But yes, so historically people were spending, I'm talking about 1970s, people were spending a lot of time. So there was always, I guess there was always that interest in how many ways you can realize a transfer function. Okay, that's a good question. I think the historical observations are certainly useful. Any other questions? Okay, so the real, okay, I guess maybe I should just spend a little time on the scaled normalized and how we get to that point. I mean, again, the scaled normalized, the original filters were derived using 10-15 pages of arithmetic, but could be just done using one line. So it's very, very, very simple, very, very trivial. We won't spend much time. So yeah, there are a few things I should talk about, but let's briefly just talk about the scaled normalized. Okay, so this is the so-called normalized lattice. In the normalized lattice, the power of each state variable inside these boxes are 1, so that's perfectly normalized. But what is not normalized are these states. If you look at these states, and then these are not normalized. Okay, so what scaled normalized does is it normalizes those states as well. So if you recall in the scaling, so if we have certain input and this is a state variable xn, and then we have the coefficient b. So what we learned from the scaling and round of noise is if expected value of x squared n was some parameter k, then we can choose a transformation t, which was square. I'm talking about as single state transformation t, which is the square root of k, and then all we have to do is change the coefficient a to a by t, and then if this is x prime n now, and then the expected value of x prime squared will be 1. Okay, that's the scaling process, right? And the transfer function remains exactly same because we multiply by t to the incoming edges, divide by t to the incoming edges, multiply by t to the outgoing edges, the transfer function remains the same. So if you think about, let's call this node, let's call this node A. So the inner product of A with respect to itself, or the power at node A. So what is A? What is the node A? A is C0 Phi0 plus C1 Phi1. C0 times Phi0 plus C1 times Phi1. So the inner product will be C0 squared plus C1 squared. Okay, so that's going to be the inner product. Phi0 inner product with itself is 1. Phi1 inner product with itself is 1. Phi0 Phi1 cross product is 0. So the inner product, if you expand that, C0 squared times inner product of Phi0 with itself, which is 1 plus C1 squared. Okay. So so what this scaling property says is that you divide these by this is k, the square root of that. So C1 is replaced by, so if C0, C1, etc. were the coefficients in the normalized lattice, in the scaled normalized lattice, we need to divide these by these and then multiply here by that quantity t. Okay, so that's kind of the first step. Okay, that's the first step. Okay, so next step we go to normalize the node B. So if you look at what is the power at node B, so the power at node B, so B is equal to C2 times Phi2 plus what was the power of node B? So the power of node B was C0 squared, this one here, C0, Phi0 and so on. Okay, so that was the initial. So the power at node B was C0 squared plus C1 squared plus C2 squared. That was the power at node B. Okay. So in order to scale that node, we have to divide by t, which is the square root of that. So we now replace this quantity by C0 squared plus C1 squared plus C2 squared. So we divide that by that. We also divide this incoming edge by same thing, C0 squared plus C1 squared plus C2 squared, and then multiply on the outgoing edge, C0 squared plus C1 squared plus C2 squared, square root. And then as we keep repeating this process, so this would have been C4, what will happen again? So this will be C3 divided by square root of C0 squared plus C1 squared plus C2 squared plus C3 squared, and that edge will be this divided by square root of C0 squared plus C1 squared plus C2 squared plus C3 squared. So like that. So that's what is called the scaled normalized lattice, where we are able to normalize not just the core part but also the numerator part. Okay, so that's let's take a quick look here. So there are these state variables that are assigned to these nodes, and basically the process that I just described. So maybe we take a quick look here. Module N. Okay, so I see. Okay, so this is the module. Okay, so this is the module N. the let's take a look what it says here. So the inner part sigma 2 0 0 0 2 2 0 2. Okay, those parts are same, k and square root of 1 minus k squared. Okay, those parts are same. What really we need to see is the edge coming that way and edge going up. So sigma 1 0 is simply for nth stage is Cn, for sigma 1 1 n is Cj squared summed over all j square root of that. Okay. Sigma 1 0 for ith stage is Ci divided by that quantity. So that's Ci, so that's Ci divided by square root of up to that quantity, C2 divided by square root up to C2 squared, C1 up to C1 squared, C3 divided by up to C3 squared. So Ci divided by sigma Cj squared, j equal to 0 to I square root, sigma 1 1, that path here. So you will see that path has a numerator and a denominator. And if you look at that quantity, the denominator is summed up to I, the numerator is summed up to I minus 1. Okay, so if you think about why is that, well, we are getting the numerator part because we are multiplying by t to the outgoing edge. So this edge itself has two characteristics. One, it is an outgoing edge of that node. Two, it's an incoming edge of that node. So because it's an outgoing of that node, I can apply that scaling property, multiply by the square root, that becomes the numerator. Because it's an incoming edge of that node, and I'm dividing by that quantity here and here, and that's why we get a numerator and a denominator. So I didn't complete that, but this would be this whole thing divided by summed over C0 squared plus C1 squared plus C2 squared plus C3 squared. Okay, so that's how we get a numerator and denominator in C3 divided by same thing. Okay, so that's really very, very simple. I can tell you this was derived in the original paper using 10-11 pages of arithmetic. But it's very trivial to derive from the normalized lattice just by using simple scaling properties. So I guess that leaves me with a few things to talk about. Few more things to talk about. I still haven't talked about how to expand the numerator with respect to the reverse polynomial. That's one thing I will talk about next class. And the other thing that I have not talked about yet is what happens if we start with pipeline transfer functions where the denominator is already in scattered lookup form. And so that will lead to, and we will see that next class, that will lead to IIR lattice digital filters which are pipelineable. If we start with the denominator in scattered lookup form, then the IIR filter will be in pipeline form as well. So we will talk about those two things next class. So again, as I mentioned, that will be the last homework when we post the homework 11. That will be the last homework and due on Wednesday. I will be away next week, Tuesday, Wednesday, Thursday. So yeah, we will see what happens to the Wednesday class. It is possible I may ask you to listen to some previous class, or it is possible if there is time, I might pre-tape a class and you can just listen to that. We will see what happens. With respect to the office hours, I may have to leave to airport immediately after the class. So yeah, we may have to cancel the office hours. But I would be still happy to see if I can have some Zoom office hours in the evening. Certainly not possible on Monday, but Tuesdays would be possible, and I will email you. So this week's homework, I'm here after the class, so please feel free to ask me questions. Your graded homeworks are here as well, so don't go away. You can collect them before you leave. Okay, so I will stop with that. Yeah, we will discuss. Let me just hand out the graded homework. We will discuss.